Hello Physics Nation, my name is Nate Larmond, and I'd like to set up an experiment on ramps. We're going to ask a simple question. How does a ramp's load and angle affect the mechanical advantage and efficiency? Or as the math teachers like to say, what is the mechanical advantage and efficiency as a function of the ramp's load and angle? So it sounds complicated, but it's really simple. There are only 4 measurements. This green arrow represents the input force. This little guy is pushing the load. We're actually going to pull it with a spring scale. This red arrow represents the weight, so you simply hang the load, and that's called the output force or the load. The height of the ramp is called the output distance, so 2 meters in this diagram, and the input distance is the length of the ramp. In this diagram, 4 meters. So with those 4 measurements, you can do all sorts of interesting calculations. But let's just back up a little bit. What is the purpose of this ramp? Why don't they just build the train tracks going right up the side of the mountain? Well, the trouble is, it would require too much force. The friction in between the wheels and the track wouldn't be enough to lift it up the side of the mountain. So they dilute the steepness. That's the phrase Galileo used. Diluting the pull due to gravity by using an inclined plane is actually a really, really old idea. The Egyptians knew to do this when they built the pyramids, and we still use it today anyway. Instead of going straight up the side of the mountain, we're going to dilute the steepness by cutting it lengthwise across the side of the mountain. Here's another ramp. Doesn't look like a ramp, but a helix or a spiral is a ramp. It's just been wrapped around a central axis, so we lift the car from ground level to the top of the parking garage here. Here's another example, similar to the train tracks. This is a road this time, except it's easy to go back and forth on a road compared to train tracks, and so these are called switchbacks. So like I said, it starts with 2 simple measurements. You hang the weight from a spring scale. In our example, this is called the load or the output force, and that's 100 newtons. We're going to pull the weight up the ramp. That's called the effort or the input force, and in this example, it's 20 newtons. This is the whole point of the ramp. It makes the lifting easier. We lift 100 newtons with only 20 newtons of force. And we're going to describe how much easier it makes the lifting with a ratio called mechanical advantage. So load divided by effort, or output force divided by input force. In this case, 100 divided by 20 is 5. That's our mechanical advantage. However, as usual, you can't get something for nothing, and this smaller force must be applied over a larger distance. In this case, the hypotenuse of the length of the ramp, the input distance, is 1.2 meters. And force multiplied by distance is work, a form of mechanical energy. So we're going to apply 20 newtons over 1.2 meters, and that means we do 24 joules of work as we pull this load up the ramp. Well, what do we have to show for it? Well, the load is at a higher state of potential energy. It's gone from this level up to this level. And so really it's just force times distance again, except the force is the output force, that is the weight, 100 newtons. And the distance is the height of the ramp, 0.2 meters or 20 centimeters. So 100 newtons multiplied by 0.2 is 20 joules of stored potential energy. So we get out 20 joules in stored potential energy, and we've put in 24. So 83% of the energy we put in is stored. We're only wasting 17% of the energy. Let's make some predictions, as we normally do. We're going to change 2 things. That is the load. We're going to pull a heavier and heavier weight up the ramp, and we're going to see how the mechanical advantage and the efficiency respond. Is it increasing, decreasing, horizontal? What sort of function? Maybe exponential, maybe... Anyway, I'm going to let you try to make a graphical prediction. The other thing we're going to mess with is the steepness of the ramp. So the output distance is the height of the ramp, and we're just going to make the ramp steeper and steeper. Again, how will mechanical advantage and efficiency respond? Okay, thanks a lot. See you in the next video.